Today we're going back to Eureka Math Module 5 and we're skipping to Lesson 20. Okay, and today we're going to be continuing what we know about two-dimensional figures by classifying them in a hierarchy based on their properties. We're going to talk about what the word hierarchy means and how we can classify something based on a hierarchy based on properties. But first, let's look at the problem of the day. As you can see, this problem of the day is reviewing the skills that we've learned before about area. It says, Nita buys a rug that is 10 3/4 feet by 12 1/2 feet. What is the area of the rug? Show your thinking with an area model and multiplication sentence. So the question is asking us to find the area of the rug. We know that the dimensions are 10 3/4 feet by 12 1/2 feet. We need to use an area model, and we need to write a multiplication sentence. So right off the bat, what would our multiplication sentence be? What would our multiplication sentence be? Brian? Very nice. 10 3/4 times 12 1/2. Go ahead and draw an area model. So after doing the area model, I see my partial products are 120, 9, 5, and 3/8. So to find the whole area, I have to do 120 plus 9 plus 5 plus 0 and 3/8. What's my fraction part altogether?
3/8.
How many ones do I have altogether?
14.
14. Good. How many tens do I have altogether?
3.
How many hundreds do I have altogether?
1.
134 and 3/8. If I look back at the problem, what should my units be?
Square feet.
Square feet. Very good. Okay, so again, this is just a review on how to use the area model to find area. If you look at our learning goal today, we are going to classify. What's another word for classify? Sort. We need to sort things out in a hierarchy. Hierarchy means there's different levels. So like, for example, at our school, we have a hierarchy, right? The principal's in charge, so she has the most power, or she's, the biggest label. Then there's me, teachers, then there's students. That's a hierarchy. Another way to think of a hierarchy is to think of different clubs that fit into other groups. Okay, for example, here's 4 terms. Student, Stockholmeyer Pandas, okay, 5th graders, and people in Miss O's class. Which one is the biggest category? Well, if you're a student, if you're a Stockholmeyer Panda, are you also a student?
Yes.
If you're a student, are you for sure a Stockholmeyer Panda?
No.
How could you be a student but not be a Stockholmeyer Panda? Talk it to the people around you. If all the students are in this bucket, right? Okay. Then what's the next biggest category?
5th grade.
Oh, the next one would be Stockholmeyer Pandas, because there are some students who don't go to Stockholmeyer, and they're Stockholmeyer Pandas. Then, some of the Stockholmeyer Pandas are 5th graders. Okay, we're going to assume that these are just 5th graders at Stockholmeyer. Then what's the most precise category? Miss O's class. Could you be in Miss O's class and not be a 5th grader? No. Could you be in Miss O's class and not be a Stockholmeyer Panda? No. Could you be in Miss O's class and not be a student? No. Could you be a student and not be in Miss O's class?
Yes.
When we draw these circles and these diagrams, let's see, hold on, no, okay. We can think of it like this. Let's say there's a person who's here. Describe that person to me. Well, they're a 5th grader at Stockholmeyer, and they are a student, but they are not in Miss O's class. Do you see that? Okay, but if I move that person, it will let me. It won't. Okay, if I take away, let's say I move that person, and I now put it here, describe that person to me. They're in Miss O's class, right? Which means they're also a student. Good. So we're going to use this concept of diagrams and hierarchies to classify two-dimensional polygons. Okay? This diagram is another version of the hierarchy, kind of like what we drew or what we did with Stockholmeyer and Stockholmeyer Pandas, right? And 5th graders in Miss O's class. So you can see if I have a polygon and it's here, okay? It's in this area right here. What names can we give it? Well, it's a rectangle. It's also a parallelogram. It's also a... So their definition of trapezoid is different. Don't worry about that. It's also a quadrilateral. Does that make sense? if I have something that is over here, that means it is a kite and it is a, okay, so this is another way to show the hierarchy. Eureka Math defines trapezoid a little bit different. They say that a trapezoid needs to have at least one pair of parallel sides. So by their definition, could a rectangle also be a trapezoid? Yes. However, for our purposes, we're going to say that a trapezoid has exactly one pair of parallel lines. So for us, is a rectangle sometimes, always, or never a trapezoid? Very good. Turn to your lesson 20 problem set. We're going to do this together. If we're going to have to write if the statement is true or false. If it is false, we are going to rewrite it to make it true. We can use our chart to help us. True or false? All trapezoids are quadrilaterals. True. Good. So we don't need to rewrite anything. Because if you look at our chart, if you are in the trapezoid area, are you also in the quadrilateral area? So it's true. Very good. True or false? All parallelograms are rhombuses. False. How could I rewrite that sentence to make it more true? Maddie?
All rhombuses are parallel.
We could say all rhombuses are parallelograms. Another way we could do it is we could say some parallelograms are rhombuses. Do you agree? Good. Number C. All squares are trapezoids. False. Why are all squares not trapezoids? How many sets of parallel sides does a square have? Two. And how many does a trapezoid have? So we can say all squares are not trapezoids. Number D. All rectangles are squares. True or false? Joseph, how could I rewrite that sentence to make it true? Wait, no. Not some squares are rectangles. Are all squares rectangles? If you're a square, are you also in the rectangle circle? So we could say all squares are rectangles. Joseph, what's another way instead of saying that? Instead of saying all rectangles are squares or all squares are rectangles, what's another way that we could fix that sentence to make it more true? Some rectangles are squares. Do you guys get it? Okay. Number E, rectangles are always parallelograms. True. Because again, if I'm in the rectangle section on our chart right here, am I also in the parallelogram section? Mm-hmm. All parallelograms are trapezoids. False. All parallelograms are not trapezoids. Very good. All rhombuses are rectangles. Is this rhombus right here also a rectangle? No. Is this rhombus right here also a rectangle? So what word might make that sentence more accurate? Some rhombuses are rectangles. This is the same as doing the sometimes, always, or never that we were working on yesterday, just with different words. We're going to skip H through J. Let's look at K. All rhombuses are squares. Is that true? Are all rhombuses squares? No. How many rhombuses are squares? All of them? None of them? Or some of them? Some. Oh, good. So some rhombuses are squares. What needs to be true for a rhombus to also be considered a square? What needs to be there? Tarun?
It needs to have 4 right angles.
It needs to have 4 right angles. Very good.